Welcome to the Royal Swedish Academy of Sciences. It's wonderful to see so many here for this press conference. The Academy has concluded its meeting and we are ready to announce this year's Nobel Prize in Physics. And as usual, I will read the announcement, first in Swedish, then in English, then the citation in German, French and Russian. I am Göran Hansson, I'm the Secretary General of the Academy, and with me here on podium is, to my right, Professor Olga Bottner, the Chairman of the Nobel Committee for Physics, and on my left side, Professor Mats Larsson, who is a member of the committee and an expert in the field of this year's prize. And later on, we hope to have one of our new Nobel laureates with us on the phone line. This year's prize is about tools made from light. Årets pris handlar om verktyg av ljus. Kungliga Vetenskapsakademin har idag beslutat att utdela 2018 års Nobelpris i fysik för banbrytande uppfinningar inom laserfysik. Med ena hälften till Arthur Ashkin för den optiska pincetten och dess tillämpning på biologiska system. Och med den andra hälften gemensamt till Gérard Mourou och Donna Strickland för deras metod att alstra högintensiva, ultrakorta optiska pulser. The Royal Swedish Academy of Sciences has today decided to award the 2018 Nobel Prize in Physics with one half to Arthur Ashkin for the optical tweezers and their application to biological systems. And the other half jointly to Gérard Mourou and Donna Strickland for their method of generating high-intensity, ultra-short optical pulses. Zur einen Hälfte an Arthur Ashkin für die optische Pinzette und ihre Anwendung auf biologische Systeme und zur anderen Hälfte gemeinsam an Gérard Mourou und Donna Strickland für ihre Methode zur Erzeugung hochintensiver, ultrakurzer optischer Pulse. Pour moitié à Arthur Ashkin, pour la pince optique et son application au système biologique, et pour l'autre moitié, conjointement à Gérard Mourou et Donna Strickland, pour leur méthode de génération d'impulsions optiques intenses ultracourtes. Arthur Ashkin za optические пинцеты и их применение в биологических системах. Gérard Mourou и Donna Strickland за их метод генерации высокоинтенсивных ультракоротких оптических импульсов. And you can see now our new Nobel laureates with us on the screen above me. Arthur Ashkin was born in 1922 in New York City. He made his remarkable invention at the Bell Laboratories in New Jersey, in the United States. Gérard Mourou was born in 1944 in Albertville in France, and he is currently at the École Polytechnique in Palaiseau in France, and also affiliated with the University of Michigan in the United States. Donna Strickland was born in 1959 in Guelph, Ontario, Canada, and she's currently at the University of Waterloo in Canada. Drs. Mourou and Strickland did much of their groundbreaking work together at the University of Rochester in the United States. Now I would like to ask the chairman of the Nobel Committee, Professor Bottner, to make some remarks about this year's Nobel Prize.
Thank you. Over the past 6 decades, lasers and laser-based devices have become indispensable in many different areas of society. With its long-range narrow beam that can be focused on a tiny spot, a laser provides high power over a small area, useful for cutting, drilling, welding, and micromachining. Other applications abound. Billions of people make daily use of optical disk drives, laser printers, and barcode scanners, or are entertained by amazing laser light shows. Millions undergo laser surgery or a laser skin treatment. The laser is truly one of the many examples of how a so-called blue sky discovery in fundamental science eventually may transform our daily lives. Today we celebrate two inventions within the field of laser physics that have opened new scientific vistas, but what's more, have already led to applications of direct benefit to society. Optical tweezers, allowing control of tiny living organisms, and an amplification technique enabling construction of high-intensity, compact laser systems. And with that, I hand over to my colleague, Professor Larsson, who will give you more details.
Yes, Mats, please.
So, Arthur Ashkin invented the optical tweezers. And he did this in 3 steps. If you look at the upper panel, he realized that he could, using the radiation pressure from a laser, and push a small, micro-sized, transparent sphere in the direction of the laser beam. He also realized, the middle panel, that because the laser beam is not homogeneous, it's more intense in the center. The sphere will be pushed into the center by so-called gradient forces. And finally, he took a lens and focused the beam so that he could keep the small sphere fixed in space. And we will now make a small demonstration of this using a hairdryer and a ping pong ball, and it will be my colleague in the committee, Anders Irbeck, who will do this demonstration. And please note now that he can tilt the hairdryer and still keep the ping pong ball under control. This is a simple test you can do yourself at home if you want. So, of course, it wasn't the fact that he could trap a small sphere that was the real breakthrough. The real breakthrough came when Arthur Ashkin demonstrated that he could trap in the tweezer, that he could trap viruses, bacteria, and even living cells. And this led to a very interesting development, very important development. And here we will demonstrate what happens if we take a molecular motor. This is a molecule that is doing work in the cell. In this case, it's a kinesin, it's a protein, and it's attached to a sphere, which is now in the optical tweezers. And the molecular motor will now start to walk on a cellular cell skeleton, but feeling the resistance from the sphere. It's like a gladiator contestant strapped with an elastic band, and you walk and it becomes more and more heavy to walk because the force is pushing you back. By doing this experiment, it was possible to measure the force between the cell skeleton and the kinesin molecule, and it was also possible to measure the step size. Now we come to the second part of this year's Nobel Prize, to Gérard Mourou and Donna Strickland. And what you see here is the development of laser pulse intensity as a function of time from the very beginning when the first laser was constructed in 1960 by my man and up to 1985. And what you see, there is first a rather sharp increase in pulse intensity, but then it levels off. And this became a problem because the technology of that time was not scalable. It was not possible to go to higher intensity because of amplifier damage. And the way to come over this hurdle was the invention of the chirp pulse amplification by Mourou and Strickland. And this was really the core of Donna Strickland's PhD thesis. So the idea and what they demonstrated is the following. You take a short pulse, you stretch it in time, maybe a factor of 1,000. And then the amplitude of the pulse will decrease, also a factor of 1,000. Then you take the pulse and send it through the amplifier. The pulse is increased in amplitude. And finally, in the final step, you compress the pulse so that it has the same duration as your input pulse, but now with a much higher intensity. And here you can see the development of pulse intensity after the invention of the CPA technique. Basically, every 4 or 5 years, the pulse intensity doubled. And this gave a possibility for a rather wide range of applications, both in basic science and in more practical applications. And here you see high-intensity ultra-short pulses. They are between 10 to 100 femtoseconds. 1 femtosecond is a million of a billionth of a second. And in the upper panel, you see very high-intensity pulses coming roughly 1 per second, like this. And these pulses can be used for laser particle acceleration. You want to accelerate electrons or protons, and this is now a development that we can already see could be of importance for cancer therapy in the future. In the middle panel, you see pulses coming roughly 1,000 per second. The intensity is a little bit lower, and these pulses are adopted to a new field of science called attosecond science. And attoseconds is even much shorter than a femtosecond, 1,000th of a femtosecond. And by using these attosecond pulses, you can explore how electrons are moving in atoms and molecules. Very short time scale. In the lower panel, the frequency has increased even more. There are now 100,000 pulses per second, but the intensity is a little bit lower. And these pulses are extremely useful for high precision measurement, high precision interaction with matter. And I give you one example how they can be used. And this is now a CPA femtosecond laser that is used to correct myopia or nearsightedness. And the femtosecond laser is in the cornea creating a small lens-shaped piece of tissue, which is called a lenticule. The femtosecond laser is also used to make a small incision in the cornea so that the lenticule can be extracted with a small instrument. And by doing this, you are decreasing the refractive power of the eye so that your focus is now on the retina and not a little bit before the retina. And nearsightedness, I can assure you, this is something I'm very well familiar with. And so finally, we are today awarding the Nobel Prize for groundbreaking inventions in the field of laser physics to Arthur Ashkin, Gérard Mourou, and Donna Strickland. Thank you.
Thank you, Mats. We may now have one of our new Nobel laureates with us on the phone. Dr. Strickland, are you there?
Yes, I am.
Hello, this is Göran Hansson again. I'm the guy who gave you the good news, what is it, 45 minutes ago or so?
That's right.
And right now we're having a press conference here at the Royal Academy of Sciences. A large number of journalists, and I'm sure they would like to ask you some questions. Are you ready for them? Yeah.
I guess so.
Thomas von Heine from Swedish television.
Yes, hello, Swedish public service television. Congratulations. I was a bit curious how you found...
Excuse me, can you hear him?
No, I'm sorry, I cannot.
There's something wrong with
Sorry about that, we lacked a microphone here. Congratulations. I was curious about how you found this. In the short introduction, it was described as a blue sky discovery, and was it, and how?
Okay. So I don't know if you also have Gérard on the phone too, but I was a PhD student at the time, just to keep that in mind. I think a lot of things, as always, is going on. Pulse compression was already going on. Different people were trying to get short pulses amplified in different ways. But I think that it's somewhat, I guess, just thinking outside the box to stretch first and then amplify. Most people were amplifying and trying to just compress whatever they had amplified. So I don't know if that answers the question.
Thank you. More questions? The lady over there. You get a microphone.
Okay. Thank you. I'm Anneli Megner-Arn from Swedish TV4. Congratulations on the prize.
Thank you.
You are the third woman ever getting the Nobel Prize in physics.
Is that all? Really?
What's your comment on that?
Okay. I thought there might have been more, but I couldn't think. Well, obviously, we need to celebrate women physicists because we're out there. And hopefully, in this time, it'll start to move forward at a faster rate, maybe. I don't know what to say. I'm honored to be one of those women.
We expect more to come.
More. Yes.
Yes, this gentleman over there.
Thank you. David Keaton from the Associated Press. First of all, congratulations. And second of all, how did you react when you received the phone call this morning? What was your first thoughts and your thoughts on sharing this prize with these other laureates?
Well, first of all, you have to think it's crazy. So that was my first thought. And you do always wonder if it's real. As far as sharing it with Gérard, of course, he was my supervisor and mentor, and he has taken CPA to great heights. So he definitely deserves this award. And I'm so happy that Arthur Ashkin also won. I think that, you know, he made so many discoveries early on that other people have done great things with, that it's fantastic that he is finally recognized.
Thank you. Yes.
I'm Per Snaprud from the daily Dagens Nyheter. In terms of...
It's a newspaper in
Sweden. It's a newspaper based in Stockholm. In terms of practical applications that make some difference in people's lives, what are your favorites from your own research?
I'm afraid I haven't done anything that was practical for somebody. I think the main practical application of CPA so far has been in the eye surgery. It was the first one, and I think it is the one that is used by the most people for something practical, and it was already discussed in the press conference. But no, I think it's still being used mostly, I shouldn't say mostly, but I think the push towards higher intensities and shorter pulses and things will lead to even more. But it's already being used for machining as well. I should say that. It does machine things like glass, just like it machines the eye.
Thank you. Are there more questions to our laureate, to Dr. Strickland? Yes, lady over there.
Congratulations. I'm Sufichen Aksasong from Green Post and China Radio. I'd just like to follow up this question, the previous question. So in which field do you think your invention can be used? Can you elaborate a little bit? Thank you.
In which field?
Yeah, that you expect further applications of the CPA technology.
Well, I mean, I think at this point it's just used almost ubiquitously in so many different ways. It is used in laser machining. The hope is that it will work. You know, very large lasers are being built around the world right now. Some of them are hoping to do laser acceleration. Some of them are hoping to, you know, cure cancer. Some of them are, you know, it seems to be just about everywhere, high-intensity lasers, just because of the way it interacts with the medium is different, and some new things are being discovered that way. But it would be in chemistry, physics, medicine, engineering.
So this development has just started, and we can expect much more to come. That's exciting news. Thank you very much for being with us, Dr. Strickland, and
thank you.
We look forward to seeing you here in Stockholm in December.
Great, I look forward to it. Thank you.
Thank you. Bye-bye for now.
Bye-bye.
Now, are there questions to the panel? I know you're eager to have your individual interviews, but maybe some of you would like to ask something while we're all here. No? Please.
Did you talk to all of this year's laureates?
Yes, we did. There was a bit of a problem with one of the phone connections, and that's why we were delayed for 5 minutes. But we've spoken to all of them. And Dr. Ashkin told us that he may not be able to give any interviews because he's very busy with his latest scientific paper. More questions? One more over there. The gentleman from Associated Press, I think.
Yes, indeed. David Keaton, thank you for the question. So this year we see a female laureate winner, as was pointed out, the third only in physics. We spoke in the last few years about female representation within this prize. I understand that you cannot talk about people that have been nominated per se, but would you be able to give us an idea of the percentage of women that are nominated for these prizes?
We have not. I don't have the statistics here in front of me. It's a small percentage, that's for sure, and that's why we are taking measures to encourage more nominations, because we don't want to miss anyone. Let me point out that these measures that we have been mentioning in the last few days is part of a long process and has actually had no effect for this year's prize. And it's important to remember that the Nobel Prize is awarded for discoveries and inventions, and those who receive it have made major contributions to humankind, and that's why they get the prize.
May I?
Please.
I mean, we cannot give you the percentages, of course, but let me just point out that the percentage reflects the number of women in science if you go back 20 or 30 years. So the number has been increasing steadily over the years, but the number of nominations rather reflect the percentages as they were, say, 2 or 3 decades back in time.
Thank you. Good point. If there are no more questions, thank you very much. Now the individual interviews, but we'll close this press conference. Thank you.